So we're going to move our attention to inverse Laplace transforms. These are in section 8.2. This is a lot like if you were taking derivatives and then you started finding antiderivatives. It's the same idea. So let's suppose we're looking at a Laplace table of Laplace transforms like the one in table 8.1. So we would have a column that says little f of t is 1. Its Laplace transform is 1 over s. So if given 1 over s, somebody might ask, what is the inverse Laplace transform of 1 over s? In other words, what's the function little f of t whose Laplace transform gives you 1 over s? So that's what that means. So the inverse Laplace transform of 1 over s is just 1. That's what this says. And we could go down our whole list of Laplace transforms we've learned. The Laplace transform of e to the at is 1 over s minus a. That means the inverse Laplace transform of 1 over s minus a is e to the at. The Laplace transform of the cosine of kt is s over s squared plus k squared. That means the inverse Laplace transform of s over s squared plus k squared is cosine kt. We're just going in the other direction. Same with sine of kt. Its Laplace transform is k over s squared plus k squared. It means the inverse Laplace transform of k over s squared plus k squared is the sine of kt. And finally, the Laplace transform of t to the nth is n factorial over s to the n plus 1 power. That just means the inverse Laplace transform of this function of s is t to the n. You just go in the opposite direction. So ultimately we want to learn how to solve some differential equations with Laplace transforms, and to do that we need to understand what it means to find the inverse Laplace transform. So here's an example. What's the inverse Laplace transform of 1 over s minus 4? So you just think back to what's my formula? 1 over s minus a. So my a is 4. That's just e to the at, which is e to the 4t in this case. Inverse Laplace transform of s over s squared plus 9. We know if we have the s in the numerator, we're looking at the cosine of kt formula. Here my k is 3. So this is just cosine of 3t. Here I have inverse Laplace transform of 4 over s squared plus 16. So this is my k is 4 in my formula for the sine of kt here. So my inverse is just the sine of 4t. It's just as simple as that. But of course, we start making them not perfect. So what if I say, hey, what is the inverse Laplace transform of 1 over s squared plus 16? Notice I have a constant in the numerator. That makes you think of the sine of kt, that formula. But what if k is 4, I need k in the numerator, so I need a 4 up there. So I can put a 4 there by multiplying by a 4, but if I multiply by a 4, I have to divide by a 4 or multiply by 1/4 out in front. This is a lot like doing some integration problems. So I multiply by the 4 there, I divide by the 4 out in front. So then this expression here is set up perfectly for the formula k over s squared plus k squared, and I just have the 1/4 out in front. So sometimes I have to manipulate the numbers a bit to get exactly what I need for the formulas. Now what about this one? The inverse Laplace transform of 6 over s to the 3rd power. So in this case, if I have s to the 3rd power, my n is 2. What do I need in the numerator? I need n factorial, right? So I need 2 factorial, which is 2. I actually have too much. I have 6. So I have 3 times 2. Just factor the 3 out in front. So this time I have too much. So I just factor the 3 out in front. That leaves me with 2 over s cubed. So the inverse Laplace transform for this is t squared, and you multiply by the 3. So we just use those properties, just manipulate the numbers to get it to match up exactly like you need it. Now another interesting one, we have a shifting property for the inverse Laplace transform. So this says the inverse Laplace transform of the shifted value of your Laplace transform is just e to the at times little f of t. Remember, capital F is the Laplace transform of little f. Now, this is what we had. This is the new formula. This is what we learned last time. Laplace transform of e to the at times f of t is the Laplace transform of little f with the argument shifted by s minus a. So this is just comparing the new to the old. This is what we learned last time. Now, so what about the inverse Laplace transform of 4 over s minus 1 squared plus 16? You look at this, you notice you have a shifted argument. So just compare it to 4 over s squared plus 16 without the shift. We know that inverse Laplace transform is the sine of 4t, because k is 4. And here we shifted, this is s minus a, that means our a is 1. So we just multiply this function, sine of 4t, by e to the t. And there's actually, when you look at your table of Laplace transforms, this is the second column. So you don't even have to think that much about it. You can look it up in the table. I just want you to know what's going on behind that table. Here's another one. This time we have s minus 3. The last time we had a constant in the numerator. When you see a variable in the numerator, you're going to think about the cosine kt formula. So we have s minus 3 squared plus 25. We clearly have a shifted argument, our s minus a. Our a is 3, same in numerator and denominator. So think about it. Just think about the cosine kt formula. So s over s squared plus k squared. Our k here is 5. So this is the same as taking the cosine of 5t and then just multiplying it by e to the at. So we'll have e to the 3t cosine 5t. So just start watching. If you have variable in the numerator, that's going to be the cosine formula. If you have a constant in the numerator, that'll be the sine formula.